Hey, good morning. Looks like we've got most everybody here, and we're going to go ahead and get started. I hope you all had a good Labor Day weekend, long weekend. I heard my dean say this morning we should have a Labor Day week instead of just one day. So he's still, I guess, suffering from not having enough time off. So I can't disagree with him. So anyway, any questions about anything before we get started on chemistry a little more today? Okay, lab this afternoon, we're going to take a look at, we're starting the skeletal system. The lab exam opens up today. It's open for 10 days. And in the meantime, we're starting new content. We're going to take a look today at the bones of the skull. And I'll have more to say about that in lab. If you were in lab yesterday, you heard me talk about the need to do a little bit every night on here because there's a lot to cover in that content, a lot to retain. Unlike a lot of things that we do in A&P, particularly in lab, the bones of the body have real relevance. This is something that once you learn them, you'll never forget them, and they'll have applications for you, throughout whatever kind of healthcare career you go into. So there's a reason that we ask you to learn all the bones of the body. So I'll talk a lot about that this afternoon in lab and tomorrow afternoon in lab too. So having said all that, let's go ahead and go back into chemistry here, and which does also surprisingly have a certain amount of relevance for us too. So let's go, here we go. And okay, we had been talking about electrons, and it's always about the electrons. But we've been talking about the electrons. The electrons are where all of our potential energy comes from in molecules. If we look at a food wrapper, and it says, for like a cereal bar, 140 calories. Well, the calories are just a measure of potential energy stored in all of the molecules of all of the sugars and fats in that food, maybe even the proteins too. So and all that is potential energy. So if you get a Nutri-Grain bar or a generic bar or something like that, it says 130, 140 calories. That is a measure of the potential energy in that bar. Doesn't mean you're going to get to use all of it, but that's what you're going to take in, 140 calories. Now, of that 140 calories, where's that coming from? Well, it is found in the electrons of all of the molecules that make up the sugars and the fats and the proteins. All of the molecules that are made of atoms, which molecules are made of atoms. Atoms have electrons. Electrons spin around the nucleus of the atom. The further away you get from the nucleus, the more potential energy you have as an electron. The valence electrons, the electrons that are involved in forming chemical bonds, not like mixtures where it's just sort of thrown together that you can filter out the ingredients. But in a chemical bond, there is a change from what you started with to what you end up with. So if you have molecules of sugar and molecules of fat and molecules of protein, every one of those is made up of atoms with electrons spinning around their nucleus. And the further away you are from the nucleus as an electron, the less energy you have to spend to get sucked into the nucleus. And so you have leftover energy, you have potential energy. And that potential energy is what our bodies can use to do things. that's where the calories are found in the electrons that are in the valence shell. That's the potential energy. And that's why we spend time talking about this. Now, if you are an atom, you have a valence shell. That's the way it is. You may have, an orbit around your nucleus. That's also called a shell. So if I say shell or orbit or orbital, I mean the same thing. Now, chemists would argue about orbitals and stuff like that, but we're going to look at this as meaning the same thing. It's where the electrons go around and around and around around the nucleus of the atom. Let me just check one thing. Okay, get back to where I was. Okay. Now, so electrons are in orbit around the nucleus of the atom. They're in orbit. They are in specified distances from the nucleus. Each orbit, each shell is a specified distance from the nucleus. And the electrons that are in orbit closest to the nucleus have to spend the most energy to keep from getting sucked in. Because after all, the electrons, while they each have one negative charge and they balance the protons in the nucleus. If you've got 10 protons in the nucleus, that's a lot of positive charges pulling on those two little electrons that are in the first shell. And so they're busy trying their very best to keep from getting sucked in. We have the first shell, we have the second shell, we have the third shell. That's, there are 7 shells altogether. We don't care because in human physiology, we're only going to deal with all the atoms found within the first 3 shells. The outermost shell of every atom is the valence shell. The outermost shell is the valence shell, and it can always hold, as far as we're concerned, it can hold up to 8 or 18 electrons. In our purposes, it's going to hold 8. We don't deal with any atoms that go out to 18, at least not in human anatomy and physiology. Whatever shell is the valence shell of an atom, the atom wants to have that shell filled. Now, the valence shell for hydrogen and helium is the very first shell. This is the exception to the rule. It can only hold 2 electrons. The very first shell in hydrogen and helium, hydrogen has 1 proton and 1 electron. It's in its first shell. That first shell is also its valence shell. Helium has 2 protons, 2 electrons. It also has 2 electrons in its outermost shell, its only shell, its valence shell. So we know that the very first shell of any atom can hold no more than 2 electrons. The only 2 atoms that only have 1 shell are hydrogen and helium. All the other atoms want their valence shell filled with electrons up to 8. They want 8 electrons. At least as far as we're concerned, all atoms want to have 8 electrons in their valence shell, except for hydrogen. Okay. All atoms want to have 8 electrons in its valence shell, no matter which one it is. Now, we're not concerned past level 3, but we have 3. So if you're hydrogen, you have 1 electron. You'd really like to have 2, because you're not completely stable until you have 2 electrons in your valence shell. Forget protons. You're not completely stable till you have 2 electrons in your valence shell. If you are carbon, which has an atomic number of 6, 2 electrons in its first shell, 4 electrons in its second shell. It wants to have 4 more electrons, so it can be stable. This is what we call the Octet Rule, or the rule of 8s. Every atom wants to have 8 electrons in their valence shell. They want to have a completely filled up valence shell. Now, if you are one of the noble gases, like helium, or neon, or argon, or krypton, or radon, you already have your valence shells filled up. Helium only has 2 protons and 2 electrons. Its valence shell is filled. Neon has atomic number of 10, has 2 electrons in its first shell and 8 in its second shell. And so neither one of those are reacting. Helium doesn't react with anything. It doesn't, chemical reactions are driven by this desire of the atom to fill up its valence shell. That's why chemical reactions occur. Atoms are trying to get 8 electrons in their valence shell. And that's what drives chemical reactions, this need to fill up the valence shell. So if you already have your valence shell filled, nothing's going to happen. Neon is considered an inert gas. Helium is an inert gas. Argon and krypton, the rest of the noble gases, that's why we call them the noble gases, I guess. Or maybe Alfred Nobel discovered them, one or the other. They are non-reactive. They are inert because their valence shells are completely full. Everybody else, though, has valence shells that are not full. And an atom will do everything it can to satisfy that rule of 8, to put 8 electrons in its valence shell. If it needs an electron, it will grab one or borrow one. If it has too many electrons, it will kick one out or share it with somebody else to keep its valence shell happy. Atoms will do whatever it takes to get a stable valence shell with 8 electrons. Yeah. It will gain electrons, it will lose electrons, it will share electrons to do whatever it can. And for the remaining 112 atoms, that's how they do it. They want to achieve stability in their valence shell. As far as we're concerned, it's only the first 3 shells. So this rule of 8 dictates, how many electrons are going to be present in every shell. And the rule of 8 also dictates why atoms react. So here we have these inert elements, helium and neon. Helium has 2 protons and 2 electrons. Don't worry about the neutrons at this point. It's balanced. Helium's balanced, 2 protons, 2 electrons. Its valence shell, which is its only shell, only orbital, can only hold 2 electrons. And lo and behold, it only has 2 electrons. So helium is stable. Neon, next to it there, has 10 protons, atomic number's 10 protons, 10 electrons. It has 2 in its first orbit, or shell. It has 8 in its second shell, or second orbit, whatever. It can only hold 8 in its second shell. It is stable. If it had feelings, it would be fat, dumb, and happy, as they say, because it has all of its spaces filled up. There is no room for any more electrons. It doesn't need any more electrons. It doesn't have to borrow an electron or share an electron or kick out an electron. It is stable. Neon can't react with anything. Helium can't react with anything. They don't react at all. That's why we call them the inert elements or the non-reactive elements. Everything else other than all except for the noble gases are the inert elements there on the far right-hand side of the periodic table in a column on the far right-hand side, starting with helium and going down to radon. They are inert. Everything else is not inert. Everything else is reactive because their valence shells are not filled up. Starting with hydrogen. Hydrogen has one electron. It would love to have a second electron. Its hydrogen, a hydrogen atom is reactive. Carbon, right next to it there, is also reactive. Atomic number 6, 2 electrons in the first shell, 4 in the second shell. It would love to have 4 more electrons to be stable. So carbon is very reactive. Carbon and hydrogen are both very reactive. Below the hydrogen, we have oxygen. 2 electrons in the first shell, 6 in the second shell. It wants 2 more in its valence shell there, and it will react with lots of compounds to pick up 2 electrons. You know, oxygen is also considered very reactive. So is sodium. Down at the bottom right-hand side, look at sodium. Sodium has an atomic number of 11. 11 protons, 11 electrons. 2 in the first shell, 8 in the second shell, and 1 in the third shell. Sodium is very, very reactive. If you've ever seen a little block of sodium thrown into water, you know what that's like. It foams and hisses and burns. It burns in the water. It's so reactive. So, but these are examples, particularly in human anatomy and physiology, of the types of atoms that our bodies encounter. Now, how do we get these electrons? If we have chemical reactions, if the need to satisfy those valence shells drive chemical reactions, how do we make that work? Well, atoms will bind with other atoms. That's the end result of a chemical reaction. Chemical reaction is either going to take reactants and give you a product. Now, the product may be larger, may be smaller. You may you may cause atoms to come together. You may break atoms apart from each other. You may take large molecules and break them into small molecules, or take small molecules and make big ones. But the end result is always going to be stability with the product. You're always going to end up with a product that is stable. And the reason that works is because chemical bonds will occur within the atoms that will make them stable. Now, the 3 types of chemical bonds are what we call the ionic bonds, the covalent bonds, and the hydrogen bonds. Now, ionic bonds are pretty simple and they're pretty weak, but they do make the atom stable. An ion is an atom that has gained or lost an electron. It is no longer called an atom, it's called an ion. It can be a positive ion. If it loses an electron, it becomes positive. For example, sodium, 11 protons, 11 electrons. If it kicks out the 11th electron, one way out there in the third shell, all by itself, not feeling any love from the nucleus. If sodium were to kick out that 11th electron, it would only have 10 electrons. Still has 11 protons. 11 protons and 10 electrons. The positive charges outweigh the negative charges. You have more positive charges than negative charges. So sodium now is no longer an atom, it's an ion, and it's a positive ion. If sodium kicks out their electron, they are no longer an ion, they are now a positive ion. Chlorine, as its counterpart, has an atomic number 17. 2 electrons in the first shell, 8 in the second shell, and 7 in the third shell. If chlorine grabs that random electron kicked out of sodium, Chlorine has an atomic number of 17 protons, but if it grabs that electron from sodium, it now has 18 electrons, which gives it one more electron than protons. 17 protons, 18 electrons. Chlorine is now a negative ion. It's no longer an atom because atoms are always balanced. Ions are either positive or negative. If you gain an electron, you are a negative ion. If you lose an electron, you are a positive ion. Because remember, electrons and protons are balanced. Gain an electron, you have more electrons than protons. You're negative. Lose an electron, you have less electrons than protons, and you're positive. So the protons never change. It's always the electrons that move around. Now, ionic bonds are not real strong. And what happens is if you gain an electron, you have a negative charge. If you lose an electron, you have a positive charge, and the positive and negative charges draw the atoms together like magnets. It's described as an electrostatic attraction. Now, think about what's electrostatic. Well, you think of static electricity, right? We've all experienced static electricity at some point. You rub a balloon across your head and your hair stands up. That's static electricity. You created a charge on the balloon that attracts the hair. Or if you've ever used a Swiffer on the floor, a Swiffer device, you rub the cloth across the floor and you put a charge on the device. By doing so, you apply static electricity to that Swiffer cloth, and that attracts the particles and dust that are on your floor, the stuff that you can't see. It's attracted to the cloth because the cloth has a positive charge and the material has the dust and debris have a negative charge, and so they're attracted to each other. The only thing wrong with those kind of cleaning aids is that we have so much dust in our houses that we can't see, that they become filled up so quickly and they don't hold the charge anymore. Other than that, they work. They do their job. They just get overwhelmed easily. This is how ionic bonds are held together. They're held together by positive and negative charges attracting each other. Now, when an ionic bond occurs, it occurs with atoms that become ions, and when they come together, they form salts. All the salts in our body are held together with ionic bonds. And we see, and if it's not in our body, salt forms a crystal. It's a crystal. Now, it is a chemical. It is a chemical bond, because when you see a salt crystal, it looks like this. You have in this case, this is sodium chloride. The large green balls are chlorine, and the little yellow balls are sodium. And they're not yellow and green anyway, but they array themselves in this, chlorine, sodium, chlorine, sodium, chlorine, sodium framework, this lattice framework, if you will. And this is what a crystal of salt would look like if we could see the atoms. So they put themselves together like this. And it forms that white crystal that we're familiar with as salt. Now, the individual atoms don't look like crystalline salt, like salt crystals. They look totally different. They look like atoms. But there is a chemical change that occurs when they come together. They form these crystals. And since sodium chloride is the #1 salt in our bodies, since we are 70% water, and that water is salt water, 0.9% sodium chloride, this is very important to us. Salt concentration is very important, and it's always about sodium chloride. All the other salts in our bodies, potassium chloride, calcium carbonate, magnesium carbonate, all those are important too. but sodium is the number one ion. Couple terms here. If you are an anion, you are a negatively charged ion. An anion is an atom that has now accepted as an extra electron. It is more negative than it was before. Before it accepted the electron, it was neutral. Now it's negative. A cation is an atom that has given up an electron and is now a positive charged ion. So, classic example of this is sodium and fluorine. Sodium has 11 protons, 11 electrons. It readily gives up that 11th electron way out there in its third shell. It's now happy. It has its outermost shell full with 8. The fact that it only has 10 electrons instead of 11 electrons doesn't bother it at all. It is now called a cation. It's positively charged. Sodium grabs that electron and puts it in its outer shell. Sodium has 7 electrons in its outer shell, and it would like to have 1 more, and that's where it gets it. And so they are attracted to each other through electrostatic charges, positive and negative charges, held together into this crystal structure, sodium chloride, sodium chloride, and totally different looking than what they did before, because the chemical change, the product is different. It's not a mixture. You can't take salt and run it through a filter and get the sodiums and the fluorines. Can't do that like you can do with sand and water. You can run a mixture of sand and water and gravel through a filter, and you can get the water out and leave the sand and gravel behind. You could filter out the sand and leave the gravel and water behind. You could filter out the gravel, filter out the sand and leave the gravel and water, whatever. You can filter out everything because there's no chemical change in a mixture. You could even take the ingredients of cake batter. You could mix up a cake, mix up all the ingredients in the batter. Everything you've done is a physical change. And theoretically, you could, because there's been no chemical change taking place here. The oil is in the batter, the eggs are in the batter, the water is in the batter, the flour is in the batter. You could conceivably, I don't know why you'd want to, but you could filter out all the ingredients of a cake batter because there's been no chemical change. You've done nothing to it except mix it together. But here, even though we see the sodiums and the fluorines very clearly in the crystal structure, they look different. They're different now than they were before. Now they form a crystal. The sodium doesn't occur as a crystal. Chlorine doesn't occur as a crystal, but now we're in crystal form. So again, ionic bonding always creates salts. The end result of ionic bonding is a salt with positive and negative ions. The cations are the positive ions. The anions are the negative ions. If you think about the cathode and anode end on your car battery, if you've ever had the opportunity to jumpstart your car or a car, the red post is the positive end, that's the cathode end. The black post is the negative end, that's the anode end. But with ionic bonding, we come together and we form a product that is different than what we started with. But ionic bonds are not the end all, and they're not very strong. You can break ionic bonds very easily. Every time you take a beaker of distilled water and add a couple 100 grams of sodium chloride to it, sodium chloride goes in the solution. It disappears. Where'd it go? It's in there. It's just that the bonds have broken. The ionic bonds have broken The sodium ions and the chlorine ions are in solution now, but they're still there. The chemical bonds, though, that we pay the most attention to, that give us all the energy from food, the calories in food, are what we call the covalent bonds. In covalent bonds, we don't take electrons from another atom. We don't give electrons to another atom. We do not alter the electron, and we don't alter the balance at all between protons and electrons. We keep the same number of protons and electrons, but now we're going to share. If you bring two atoms together, for example, two atoms of hydrogen. Hydrogen has one proton and one electron. If you bring two atoms of hydrogen together, they will react and share those two electrons. Each atom of hydrogen has one electron. If we form a molecule called H2, we have two protons and we have two electrons. The electrons, however, are moving at the speed of light, and so they can circle the nucleus of the first atom and circle the nucleus of the second atom, and it appears, because they're moving so rapidly, that there's always two electrons in the valence shell of the first atom and always two electrons in the valence shell of the second atom, because they move so rapidly because they're here and there practically at the same time. We haven't gained any electrons, but we've achieved a stable molecule. Atmospheric hydrogen is very stable. Atmospheric hydrogen is H2. It's the stuff that's in the air we breathe. It is two atoms of hydrogen gas. Each atom contributes a proton and an electron. Protons for each atom stays in the nucleus. But we have two electrons, and they spin so rapidly. They spin around the first atom, they spin around the second atom. They achieve that stability that the atom wants. H2 is not reactive, at least not very reactive anyway. So we'll just say it's not reactive because it has achieved the stability of having its valence shell full. Not all the time, but so rapidly that we can't tell when it is full and when it isn't full. So the atom acts as it's full all the time, because at 186,000 miles per second, and it's traveling, an atomic distance, which is extraordinarily tiny. So small we can't even comprehend it. To us, for all intents and purposes, it is there all the time. So covalent bonds are extraordinarily useful because they're always sharing electrons. Most common type of covalent bond that we encounter is when we share two electrons. Call that a single bond. It's a very powerful bond. We're going to share those electrons. If we share four electrons, we have a double bond. And we'll see some double bonds in very large molecules shortly. If we share 6 electrons, we have a triple bond. And the only molecule that immediately comes to mind with a triple bond is nitrogen. Atmospheric nitrogen, N2, 2 atoms of nitrogen. The atoms of nitrogen are held together with triple bonds. The stuff we're breathing, the nitrogen that we breathe is very stable. We don't breathe elemental nitrogen or elemental hydrogen, meaning an element at one atom, one atom of hydrogen, one atom of nitrogen. We don't breathe that. We breathe the atmospheric version, the stable version. N2, H2, O2. We refer to O2 as oxygen all the time. O2 is 2 oxygen molecules together. Two oxygen atoms together sharing electrons through a double bond. So that it achieves the stability it wants in its valence shell. it shares 2 electrons with atom number 1 and atom number 2. So everybody, the oxygen molecule is very stable. So the atoms, with a covalent bond, every atom involved in the bond has its valence shell filled up at least part of the time. And so that makes it very, very stable. We don't, as I said, we breathe the atmospheric version of these gases that are held together with covalent bonds. And it's extremely stable. Okay. Now, if you are a covalent bond, you occur in one of 2 ways. You are either a polar bond, meaning that you have a very slight unequal distribution of the electrons. You're still sharing and you're still stable, but the orbit may be a little more elliptical, drawing the electrons down a little closer to the nucleus of another atom. Everybody's still happy. Every valence shell is still filled, but the sharing may be slightly unequal. Nonpolar bonds don't have that problem. Most of our covalent bonds in molecules that we deal with are going to be nonpolar. So here's a covalent bond. Here's hydrogen. Up at the top, we see each one of those with the big red plus, red and white plus, is a hydrogen atom. They're held together. The 2 hydrogens are held together with a covalent bond. They are sharing their electrons. Each hydrogen atom contributes 1 electron. These electrons orbit the nucleus of each atom so rapidly that the sharing is so fast that both atoms see it as complete stability in its valence shell. 2 electrons on the left, 2 electrons on the right, 2 electrons on the left, 2 electrons on the right. We're moving so rapidly with those electrons that we can't distinguish. I mean, we can in the animation, but they're moving so fast that we can't distinguish where the electrons are not, as opposed to even where they are. So the atoms are stable because, at least, as I say, at least for part of the time, their shells are filled up. And part of the time happens a lot because they're moving so quickly. We even see it down here. If we look at the bottom, we see an example of an oxygen atom picking up a hydrogen. It's going to form a covalent bond with the hydrogen. Here comes hydrogen on the left-hand side with its 1 electron. Here comes oxygen with its 8 electrons, 6 in its valence shell. The hydrogen binds covalently with the oxygen, and now the hydrogen has 2 electrons that can spin around it because it's sharing with the oxygen. And the oxygen has 7 electrons that will spin around it. 7 electrons in its valence shell that it's sharing because the hydrogen is sharing with the oxygen. Not 100% stable. The oxygen's not 100% stable because it still has room for 1 more electron, but it's more stable than it was because it's, and the hydrogen is now stable because it has 2 electrons in its outer shell, its only shell. The whole purpose of covalent bonding is to satisfy this octet rule, to fill up 8 electrons in whatever shell is the valence shell, except hydrogen. Of course, hydrogen only needs 2. Hydrogen's the exception. But everybody else wants to have 8 electrons. Okay, covalent bonding gives you 8 electrons in your valence shell. You're sharing. You're technically not adding any electrons or taking any away because you're sharing. And so the valence shells become full briefly, on and off, again and again and again. Now, two of the most reactive atoms that we deal with um, from human anatomy perspective and physiology perspective is hydrogen and sodium. I'm sorry, carbon. Sodium is pretty reactive. We'll talk about that later. As far as covalent bonding goes, we have carbon. Carbon has 6 protons, 6 electrons, 2 in its first orbit, 4 in its second orbit. It would love to have 4 more electrons in there to achieve 8, like the Octet Rule says. Hydrogen, over on the left, has 1 electron in its valence shell, its orbital, its outermost shell. It would like to fill up that valence shell. It would like to have 2 electrons in there. So we see carbon wants 4 more electrons to put 8 in its valence shell because it has 4 now, and you know it can hold 4 more because the second shell of any atom can hold up to 8 electrons. Carbon wants to have 8 electrons in there to achieve stability. It will react with hydrogen. Carbon reacts with hydrogen very easily all the time. Here we see a carbon atom up here. We got the electrons slowed down a lot. But there's the first shell with 2 electrons. There's the second shell with 4 electrons. There's room for 4 more electrons in here. Where's it going to get the 4 electrons? It's going to covalently bond to hydrogen. Where's hydrogen going to get the extra electron for every hydrogen atom? It's going to be covalently bond with the carbon. And so what will happen is that as the hydrogen binds to the carbon, the hydrogen brings its electron in, and carbon will share 1 of its electrons with the hydrogen. And now we have 2 electrons here. And those 2 electrons will spin around the hydrogens and spin around the valence shell of the carbon. And if we do it again, we have 2 electrons that can spin around the hydrogen and 2 electrons that can spin around the valence shell of the carbon, and it happens again and again. And so we end up with a totally different compound, a totally different molecule. By stringing together 4 hydrogens with a carbon atom, we no longer have the properties of a carbon atom and the properties of a hydrogen atom. We have a new molecule called methane. This is methane gas. We write it as CH4, 1 carbon, 4 hydrogens. Or the diagram over here shows you, it looks like a little plus sign with the hydrogens at 90-degree angles to each other. And so this is methane. Now, methane gas has a great deal of potential energy. All those electrons that are being shared in here have a great deal of potential energy, and we can use that. What do we use methane gas for? Its common name is natural gas. We cook with it. We power vehicles with it. We wash our dishes with it. We use it for hot water, for showers. We fire up our fireplaces with it sometimes. We heat our houses with it. Natural gas is a very useful, methane is a very useful molecule. And the energy that is contained in methane is the potential energy from all those electrons in their valence shells around the nucleus of each of the atoms. Now, the molecule of methane gas is totally different than the individual atoms that made it up. But you combine all those atoms, now you have a molecule with lots of potential energy. We do all sorts of things with methane gas. There's even more useful gas than that, and that's propane. Propane, the stuff you have in a tank that you hook on your gas grill, or if you live where you don't have natural gas lines coming to your house, you have a tank in the backyard or behind the house that contains propane for your fireplace, for your hot water heater, for your furnace, for your stove, for your clothes dryer. It's even more efficient than, has more energy available than methane, because propane has 3 carbons and 8 hydrogens in its formula, meaning it has even more electrons available with even more potential energy. So propane is another one of these molecules that we use all the time, because we can burn it. We can release that energy in a controlled manner. So this is where this potential energy is really going to come into play. Yes, we see it in the calorie content of the food that we eat, and that's great. We also see its application here in methane or in propane. Consider gasoline or diesel. Lots of covalently bonded molecules in the gasoline or in the diesel with lots of stored potential energy. Okay, we call it chemical energy. That's what methane is. It's chemical energy. When we burn fuel in our vehicles, it releases energy for us to do things, to make our vehicles move. And that's all because of the electrons and their potential energy here. Now, certain molecules that are held together covalently have what we call a very specific shape. Carbon dioxide is a little bit of a ringer here. Carbon dioxide is in a straight line. Many of the molecules are twisted around and bent a little bit. Glucose, for example, is usually in a hexagon shape. It has 6 carbons, so it tends to form a ring. That's fine. That's how glucose operates. Sucrose, table sugar, is a double ring. Carbon dioxide, a little different. It's in a straight line. An oxygen, a carbon, and an oxygen. It is symmetrical. It is linear. It's different. Doesn't affect its ability to do what it does. It's just different. However, carbon dioxide is considered a non-polar molecule. As the electrons are shared between the carbons and the carbons and the oxygens, the distribution, the sharing is balanced. The sharing is balanced. The same with glucose, sugar. The sharing is balanced. The electrons are shared equally. There are no positive and negative ends of glucose. There are no positive and negative ends of carbon dioxide. However, we do have polar molecules that are held together with covalent bonds. With a polar covalent bond, you have unequal sharing of the electrons. One end of the molecule tends to have a positive charge, and the other end tends to have a negative charge. They're very slight charges, but they're there simply because of the unequal distribution of the electrons. If you are strong enough to attract electrons, you have a strong attraction to electrons, you're electronegative. Atoms with lots of protons in their nucleus will attract electrons. They're electronegative. Atoms with less protons in the nucleus are electropositive because they will draw less electrons. Because even though the size doesn't matter in the atom with electrons and protons, the charge does. If you have 10 protons in the nucleus, each one of those is a positive charge. You got one little itty bitty electron over here with its negative charge fighting off those 10 protons. The 10 protons is a pretty powerful pull on that one little electron. The best example of a polar bond is a water molecule. Water molecules are hydrogen and 2 hydrogens and 1 oxygen. The hydrogens always angle themselves apart at an angle that's a little greater than 90 degrees. It's actually about 104 degrees. If you want to always remember the shape of a water molecule, draw a picture of Mickey Mouse. It's Mickey Mouse's head, the ears and the face. The ears are the hydrogens, the face is the oxygen, and separate, you know what Mickey looks like. That's what a water molecule looks like. Sort of like this. Anyway, oxygen is electronegative. And when oxygen and the hydrogen combines to form water, the charge from the protons in the nucleus of the oxygen atom tend to draw the electrons, all the electrons down towards the nucleus. Now that doesn't happen when oxygen's by itself, because it's pretty balanced. The electrons in its valence shell do a pretty good job of resisting the pull of the protons. But when you have hydrogens combined there, now you have not 8 electrons, but you've got 10 electrons, because you've got the 2 from the hydrogens in the water molecule. They tend to gravitate down towards the nucleus. Now they don't get pulled into orbit around the oxygen and get stuck there. They still orbit each of the hydrogens to keep the hydrogens happy. But what's going on is that these electrons all tend to have a more of an elliptical orbit, which spins around the oxygen atom more frequently. The end result is that it gives a slight negative charge. All those electrons are being pulled down towards the protons, and it makes the oxygen end of a water molecule slightly negative. We call it a dipole. There's 2 different ends. A battery is a dipole, it has a positive and a negative end. Water molecule is a dipole, it has a positive and negative end. The hydrogen ends of a water molecule are positive, the oxygen end is negative, simply because we are having a slight shift of the electrons. They're still satisfying covalent bonding. They're still satisfying the valence of electrons, the valence shells of the hydrogens and the oxygen, but the electrons are slightly distorted in their orbits so that they spend a little more time around the oxygen. The oxygen end of the water molecule is slightly negative, and the hydrogen ends are slightly positive because you're pulling the electrons away from the positive hydrogens. And this allows the formation of what we call a hydrogen bond. Hydrogen bonds are very weak. They break all the time. The positive end of a water molecule will be attracted to the negative end of another water molecule. The positive hydrogen is drawn towards the negative oxygen magnetically. And so every water molecule will be attracted to, every water molecule has 2 hydrogens and an oxygen. The 2 hydrogens are attracted to the oxygen ends of 2 more molecules. The oxygen end of the water molecule is attracted to another, or maybe 2 more hydrogen ends. And so it forms bonds like this. Now, this is a very weak bond. Just think the hydrogen end is attracted to the oxygen end of another water molecule. What this does, though, while it's a very weak bond and breaks all the time, this is what allows water to be a liquid and not a gas. Water is held together by hydrogen bonds. If you have a beaker of water and you pour it out on the desktop, it's not going to suddenly dissipate into the air. It's going to form this big puddle on the desktop. It's going to spread out. You're going to see drops of water everywhere. You're going to see drops of water in the inside of the beaker. You see that adhering to the surface of the beaker. Water holds together thanks to these hydrogen bonds. Large molecules like DNA, for example. The DNA molecule is about 6 feet long. if you could have one strand of DNA and the histone and the DNA, the chromatin. The chromatin, each individual chromatin strand is about 6 feet long, but it's a curled double helix within 6 feet of this double helix where it's curled around each other. It is the hydrogen bonds that occur between the molecules of a strand of DNA that cause it to turn and twist like that. And so molecules have large molecules have very specific shapes, and the shape is caused by the bonding that occurs with these hydrogen bonds. And while it's not a very strong bond, it is strong enough to twist a molecule. It's strong enough to hold water together. Strong enough so that water forms a puddle, or sticks to the side of a beaker or glass. It provides the surface tension that holds water together, as well as very large molecules too. Okay, this should work.
The atoms that make up a water molecule are in a constant tug of war. Oxygen is a fast
If you consider, if you could take a pan of water and place it on the stove, and you turn it on high, it takes time for that water to boil. Boiling requires the breaking of these hydrogen bonds. So you're applying energy to the water molecules. To get it to boil, you have to break those bonds. You have to get that temperature up to 100 degrees Celsius or 212 degrees Fahrenheit to get that water to boil. It doesn't start instantly. You can't put the pan on the stove, turn it on high, and watch it and expect it to boil instantly. It doesn't work that way. You have to apply energy to that system to break those bonds. The same thing applies to freezing water. These molecules are moving around all the time. They're moving around, they're bouncing around, they're spinning around each other, and there's a lot of action going on here. To get water to freeze, you have to take away enough heat energy to slow those molecules down. And it takes time. If you have an ice maker in your refrigerator and you hear the water going into it, when it reloads, you know that it still has to take time for that water to freeze. If you have ice trays and use ice cubes, it still takes time to get water to freeze. But you have to lower the temperature enough that these individual molecules here slow down and stop moving. And then that's when freezing occurs. And you have to get down to 0 degrees Celsius or 32 degrees Fahrenheit to get water to freeze. So you have to take a lot of energy out of that. You want to heat energy away. Water moves all the time. One last type of bond that occurs is called van der Waals attraction. And we see it in one particular area that affects us. It usually occurs, this is something we see in nonpolar molecules. So if you have a molecule that is balanced, for example, the electrons are moving around the individual atoms in the large, particularly in large molecules. The electrons are moving around the individual atoms in the large molecule, and randomly and occasionally we may see one side of that molecule become slightly positive, while a molecule adjacent to it becomes slightly negative, and they are attracted together. And so if you have large molecules that are close to each other, and one side becomes slightly positive and one side becomes slightly negative, they are attracted to each other, and they will briefly bind together. It's a very, very weak bond. This is 1% of the strength of a covalent bond. Now, where do we see it? Well, if you look at butter or lard or animal fat, any kind of animal fat is solid at room temperature. Butter is solid at room temperature. Lard, which is rendered fat, is solid at room temperature. And we call it animal shortening, if you will. Those are all solid at room temperature because they are made up of very large molecules called fatty acids that are very close together in long chains, and randomly and occasionally, occasionally, the electrons change the charge briefly next to these molecules, and they stick together. And it happens frequently enough that an animal fat is a solid at room temperature. Butter is a solid at room temperature, even though it will melt if you leave it out long enough. But it won't melt away, it'll just get squishy. Animal fat that you trim off of meat is a solid at room temperature because of van der Waals attraction. Lard, animal shortening, is solid. Now, plant fats don't exhibit van der Waals attraction. Plant fats are not solid at room temperature. Plant fats are liquid. In fact, all of our oils, our cooking oils, are all based on plant fats, or most of them. Most are based off of plant fats. Let me rephrase that. The healthy ones are based off of plant fats, like corn oil and safflower oil and olive oil. Things like this. What we euphemistically refer to as vegetable oil. These are all plant fats. Plant fats don't exhibit van der Waals attraction. So plant fats are liquid, always liquid at room temperature. So no van der Waals attraction. Okay, so now we know why atoms will react. They want to react to achieve stability in their valence shell, either gain an electron, lose an electron, or share an electron. We know that most of them like to share as opposed to anything else. So these reactions occur to do that, to achieve that. A chemical reaction occurs when chemical bonds, as it says here, are formed, rearranged, or broken with the goal to achieve stability in the valence orbital. That's sort of left unsaid. So we have a chemical reaction that takes place. Sodium and chlorine coming together to make salt is a chemical reaction. Hydrogen bonding that occurs between oxygen and hydrogen is in water molecules is a chemical reaction, because the individual hydrogen atoms and the individual oxygen atoms have totally different properties in water. Any chemical reaction can be written out in an equation, and you're always going to see the reactants and the products. Reactants are what start the reaction or go into the reaction, and the product is the end result. Hydrogen and oxygen are the reactants, and water is the product. Or water is the reactant, and hydrogen and oxygen are the products. And typically, in chemistry, the reactants and the products are balanced. Doesn't work that way in the human body. End results are going to be different, because we deal with extraordinarily small concentrations of reactants and products. So and we use up our products instantly. So it's impossible to have the same, we don't have the same criteria for chemical reactions in the end result as a chemist will. Now, when we look at an equation, we use the molecular formula of a reactant or a product. So, for example, H2O, water. Everybody knows H2O is water, 2 hydrogens, 1 oxygen. Or C6H12O6, that's glucose. We use, that term will be ingrained in your memory by the time you're done with this class. C6H12O6, glucose, simple sugar. It is the source of all energies in our bodies. We use glucose as our fuel to obtain energy. And the C6H12O6 tells you that glucose has 6 carbons, 12 hydrogens, and 6 oxygens. So that is the molecule of glucose. When we have a chemical reaction taking place, we have 3 possible common outcomes. We have what's known as a synthesis reaction, where you take small molecules and react them together and make a large molecule. Glucose and glucose together gives you fructose, gives you maltose. Glucose and fructose together gives you sucrose, table sugar, the stuff that's in the little white packets that you get at Waals when you're getting your coffee in the morning, for example. Those little packets contain, it says sugar, it says granulated sugar. That is sucrose. That is a glucose molecule and a fructose, which is another 6-carbon sugar linked together. You had a chemical reaction to take glucose and fructose to give you sucrose. It is what we call an anabolic reaction. It's an anabolic process. Anabolic reactions build large molecules from small ones. 2 simple sugars will give you table sugar. 2 simple sugars give you table sugar. Fructose is a simple sugar. Fructose, high fructose corn syrup is what is in our soft drinks, in Coke and Mountain Dew and stuff. That's the sweetener. We haven't had cane sugar for years in soft drinks. So high fructose corn syrup is our sweetener. If we take fructose, 6-carbon sugar, and glucose, another 6-carbon sugar, react them together, they'll give us table sugar, a bigger molecule. Sucrose is 12 carbons, not just 6. The decomposition reaction is just the opposite. You break something down. You take a large molecule, break it down. This is what we call a catabolic reaction. Catabolic reactions break things down. Anabolic reactions build things up. If you eat something with sugar in it, the commercial, you're not yourself if you don't eat a Snickers bar. Well, Snickers has got sugar in it. It has table sugar in it, sucrose. as well as fats in there, and and protein in the peanuts. As far as snacks go, a Snickers bar is not bad. Nothing is bad for you to eat as long as it's in, it's all about quantity. You know, how much do you eat? How often do you eat? We're going to go into that much later on. Anyway, you eat the Snickers bar. It has, energy. It has calories in it. You break down the sucrose, the table sugar, into glucose, and now you can break the glucose down and release energy. Catabolic reactions take large molecules and break them down to smaller molecules. Decomposition. Catabolic reactions. Important term to remember, anabolic and catabolic. Anabolic is building up, catabolic is breaking down. Third type of reaction are exchange reactions. You're building something up at the same time you're breaking something down. You're breaking bonds and you are making bonds at the same time. For example, when you break down glucose, you can have a catabolic reaction to break down glucose, but your products of breaking down glucose are going to be the production of carbon dioxide and water. So breaking one down and building something else up. Exchange reactions have both a synthesis side and a decomposition side, or an anabolic side and a catabolic side. You could, for example, you can, if you're low on blood sugar, you can take glycogen, which is a stored compound in our liver. It is the animal version, the human version of starch. We don't store carbohydrates as starch. We store carbohydrates as glycogen. It's similar to starch, but it's the human version of it. So, and we can break that glycogen down into glucose. That's a decomposition reaction. On the other hand, if we take in a lot of glucose in our diet, we can take that excess glucose and store it in our liver as glycogen. We can go back and forth and do this at the same time. Another type of reaction that occurs in the human body is something called a reduction oxidation reaction. We call it a redox. Now, atoms, and this is where we get into chemist talk, atoms are considered to be reduced because it's a reduction oxidation reaction. Atoms get reduced when they gain electrons, and they're oxidized when they lose electrons. Oxidation. You have a fire pit, and you're burning wood in the fire pit, and you take a big log and throw it in your fire pit, and it burns. The log is being oxidized. It's when you're burning a log, you are breaking covalent bonds. When you break covalent bonds, you release energy. Burning your log, you get heat and light. When you're breaking the covalent bonds, you are releasing the electrons. So when it's being oxidized, it's burning. It's giving up its electrons. That's oxidation. Where do those electrons go? They don't just go randomly out into nowhere or out into the universe. The universe doesn't like that. The universe has to stay balanced. The electrons have to go to another atom. Some atom has to grab those electrons coming off of the log. Because if you're going to burn that log, you are going to break covalent bonds. The covalent bonds holding the log together, because logs are really mostly carbohydrates anyway. The cellulose and lignin are what make up a log. So you're breaking those covalent bonds, and releasing electrons. Electrons give you heat and light as they come off of the log. You also get gases that you can't see. Now the electrons are releasing the heat and light, when you're burning the log. Where do they go? They get grabbed by oxygen. Electrons are grabbed by oxygen in the air. They form water. They form carbon dioxide. And they they don't get lost. They get picked up. Because if you take your fire pit and you were to put an airtight cover over the fire pit, what would happen? The fire would go out, because you would cut off the source of oxygen and you would allow carbon dioxide to accumulate in the fire pit, and there'd be no place for those electrons to go. So nothing's ever simple, or as simple as we think it is. We burn a log, we think, hey, we're burning a log, great. Well, it's actually a very complicated chemical reaction taking place there. You raise the energy level of the log to where it starts to combust. You are freeing the electrons when you're breaking the covalent bonds within the log. The electrons are running free until they're grabbed by the oxygen that's in the air around them. So the oxygen becomes reduced. When oxygen is the electron grabber, if you will. And when it grabs electrons, it gets more negative charges and it becomes reduced. Chemists call it reduction. I don't know why. They say it's reduced because it has, they say the number of positive charges are less than they were before. So, okay, fine. For a chemical reaction like this to occur in our bodies, when we oxidize food, we have to have oxygen available to grab the electrons that are coming off of the food that's being oxidized. When we break down glucose, we are breaking covalent bonds in glucose, releasing energy, releasing electrons. Those electrons have to go somewhere. They have to get grabbed by oxygen. Oxidation and reduction. We'll talk a lot more about that in chapter 24. So a couple of things here. Go with our catabolic and anabolic reactions. Chemical reactions are either going to be exergonic or endergonic. An exergonic reaction gives off energy. You're going to burn that log. You're going to release energy. You're going to eat that Snickers bar and release the energy in its covalent bonds. In burning the log, you're going to release the energy in the covalent bonds holding the log together. You give off the energy that was stored in the valence shell electrons. And you're going to release that potential energy and turn it into kinetic energy. An endergonic reaction requires energy to build up. You have to store energy in the valence electrons. An endergonic reaction uses energy. A log, if you have a tree and you cut in and you have a branch that fell off the tree and you burn that, well, that tree contains stored energy from sunlight that was, absorbed by the leaves and goes into the branches of the tree and so on. That's stored energy. You're going to release that. Or let's go back to our cake example. You take your batter and you create your cake batter, the flour and the sugar, the water, the eggs, the oil, the flavoring, I have no idea what it goes into a cake batter. My wife could tell you, but cake batter is nothing more than a mixture. However, if you put it into a pan and put it in the oven and turn the oven on, important point, I won't explain why, and set it to 350, turn it on, that batter will convert, will have a chemical change into cake, which now the end result, the end product is totally different than what you started with. You can't take cake and filter out the different ingredients because of the chemical change. It has greater potential energy now than we started with the batter. So an endergonic reaction uses energy and stores it in the molecules. An exergonic reaction gives off energy. These chemical reactions in our bodies are not reversible. Chemists will tell you that a chemical reaction is always reversible. You can go from reactants to products and back to reactants again. It doesn't work that way. Our energy demands are so high that as soon as we make a product, we use it up. When we use reactants and get a product, we can't go back. We remove them. If we take glucose and react it, we burn glucose in our bodies in the presence of oxygen, we create carbon dioxide and water. And theoretically, carbon dioxide and water with energy could form glucose again. That's how plants do it. But A, we have such small quantities, and B, we've already used up the energy, and we've already released the carbon dioxide and water. Okay, we're going to stop here, and I will pick up on this Monday. Okay. That's right, we only get one lecture in this week. So, as I said, lab this week is all about bones. Today we'll be looking at the bones of the skull, and then we'll continue on with this. The lab test is open for the Wednesday lab. It opened up today. So, and I'm going to get us out. It's 11 o'clock. I'm going to get us out of here. And thank you very much for being here today. And this will get posted in YouTube.